Okay, so 2.5 is quite an important section because it's solving problems involving rate of change. And they give you this example of a profit model, which is obviously an upside down parabola. So I'm just going to put that in here right there. Profit of x is equal to minus 60x squared. I think it was plus 1800. Let's see, x. I think it's plus 1800x plus 16500. And I just want you to notice something. So if the x-axis, let's see if that was correct. Yeah, so we'd have to put it the y in different terms here. Goes as high as 16,500 and steps of 1,000. There we go. If you notice a parabola downward facing will always have a highest peak. And now let's just look very quickly at this. If the y-axis measures profit, which this indicates, notice the left side here will always be the y-axis, and this right side, the x values, represent the price of a ticket. So this is, I believe, they're selling, I forget what they're selling. It's a theater selling tickets. So this is in dollars, and this is just number of tickets that they sell. Notice that if it's represented by an upside down parabola, there is a highest profit point. Where will that highest profit point be? It'll be the highest point on the y-axis. Where is that? At the vertex, which means if profit is represented by an upside down parabola, the vertex represents the time when you will maximize your profit. Now notice when they sell 15 tickets, they make $30,000. Therefore, 15 tickets is their best option. When they sell more or less, they don't make as much. You might say, well, how can you make less selling more tickets? Well, some profit models in that, good examples, medicine. You'll see medicine in the States go up and down because it's unregulated, which means you can set any price you want. So if a company can sell 10 pills at $10,000 or $1,000, which will give them a profit of $10,000, they would rather do that than sell 1,000 pills at $10, which would give them the same profit. Why? Because the materials, ingredients, and labor required to make 10 pills is much smaller than it is to make 1,000 pills. So businesses go through all these cost models to figure out what's the highest price they can charge and still make the same profit, which is why really you shouldn't have medicine under free enterprise, but that's a different discussion. What's interesting about this in the free enterprise model is that based on this, you can see, let's say 1,000 people desperately needed that pill. That means 900 people are not accessing medicine, which means 900 people get sick, which means their work productivity goes down, which means the economy goes down. So what's interesting about this is while up here the whole point is to get your most out of your economy, on a global scale, when you consider all the job markets, it actually has a negative impact on the economy. And I'm always fascinated that capitalism doesn't take that into effect, that even though it's a-okay to charge whatever you want, you're actually hurting your overall economy. It's why they in other countries, including Canada, we have what's called regulation maximizing. It's called the prescription, I think it's the Regulated Prescription Bureau, in which we put a max cost. We say to drug companies, you can only charge whatever it is, $40 for this pill. And they don't care because they're getting the majority of their profit from their main country, USA. But it's also why a lot of people in the States cross the border and shop at Canadian pharmacies, and even governors in the northern states have encouraged them to do so. It's kind of sad. And also, you'll notice that our prices are slowly going up as our politics get influenced by the same politics that change the regulations in the States. That is a big aside, but my point is here the vertex represents the best profit, and it's a good example of as you manufacture more of something, sometimes your profit margin goes down. Clothes, other things as well. What do the x-axis represent? Well, if everything above this is profit, and that's all positive above the x-axis, and down below is all negative. The x-axis represents the point of when you start selling things and start making a profit. Now, obviously, over here it's at -7 something, so that doesn't matter. We can actually see at 0, somehow they're already making a profit, so this isn't quite a realistic model. But let's put that aside. Generally, we're going to ignore the left side because we don't sell negative tickets. And we can see that they're over here at about 37 or so is when they start losing money. After 37, so about 38, they start losing money. That's called the break-even point. These 2 points are called the break-even point. Now, it might be possible that a more realistic model would shift the whole thing to the left. Let's see if I can do it just by doing that. No, I can't. Maybe I can do it by doing that. Almost. Let's put that at 9. See if that does. There we go. So this model is all over to the right, and you can see the break-even point here is at 1.024, and the break-even point here is at 42.9, which means they start making money when they sell over 1 ticket, and they start losing money when they sell 43 tickets. Break-even points are another aspect. So you'll discover in this, the reason I feel this is important is it leads into calculus. It leads into calculus. And you'll want to study your standard format for parabola, which is ax squared plus bx. You want to get very good at that, plus c, which generally only tells you the y-intercept is at 0, c. And I believe you can also find the x value of the vertex and you might want to look this up because I'm not quite sure, minus b over 2a. The next one is the vertex format, which obviously will tell you the vertex, and this will tell you max profit. So if it's a max profit question, you know you need the vertex format, or you need to find the vertex. Then there's finally the factored format, and the vertex format is y is equal to a x minus h squared plus k, I think they call it. I think that's it. The factored format is y is equal to a x minus, I think they have different numbers, like they have p and x minus r or something silly like that. But it doesn't matter what these letters are. We can just call them b and c if we want for now. And the format factor is obviously something you need to do if they ask you what the break-even points are. And that's why I bring it up. So you need to be very good at converting, because they're almost always going to give it to you in the standard format, as they've done here, right? Up here, before I screwed around with it, that's the standard format. So you need to be able to find the vertex out of that. One of the ways you got to do right away is you've got to take out that minus 60. So you get x squared minus 30x, and then you can just do like that, plus 16,500. There we go. So that's the factor for it. Now that I've got it like that, I can easily come up with my vertex format. It's going to be half of that. So I'll make my g of x, just a new one, in case I mess it up, is equal to minus 60. So I'm going to do half of that, minus 15, and I know that's going to be squared. And I also know that I'm going to produce an extra number in there that I don't want, which is going to be the x squared. What's 15 times 15? It's 225. So that means I'm going to have another number in there that I don't want. It's the 225, so I have to subtract the 225, and then I can't forget this thing out there. So you can see that all these are the same. And this isn't quite perfect yet. I've got to get the minus 225 out of there. So to do that, I have to multiply it by the minus 60. And when we multiply minus 60 times 225 minus, it comes out to 13,500. So to get rid of that, to get it out of the bracket, I have to add another 13,500. And if you don't remember how to do this, Google finding the vertex format. And finally, I've got to add those two together. So that adds up to, I believe, 30,000. So finally, we have the vertex format, and lo and behold, look at the vertex 15, 30,000. And if I label it, There it is. Now, you might have said, well, I already had that for modeling, but during a test, you're not going to have desmos. You're going to have to be able to figure it out. Now, there's one way to do it, which I really like, is once you discover this minus 15, instead of doing that very complicated process we did there, once you discover the that plus 15 is the vertex, because it's the opposite, right, for the x transformations, you can take the 15 and plug it into this formula to get the y value. So what is P of 15? It's 30,000, which means I could forget all that calculations I was doing and just slap on a 30,000 here. So once you figure out this internal part with this factored out, you instantly get the x value of the vertex. You can plug it into the original formula, which will spit out the y value of the vertex. You can just slap it on the end. That's called partial completion of the square. I actually love it. It's a lot faster, especially if you have the formula already set up like that. So those are the skills you're going to need for this chapter. Let's get on to the questions. So obviously they're trying to get you to calculate the average rate of change as you get closer and closer to 15, which means that if we look at it carefully, as we go up on the left side closer and closer to 15, the slope is going to get smaller and smaller. See, it's the same as the tangent as we get closer and closer, and it's going to be positive. And as we pass 15 and start doing it on the other side, it's going to be this way and this way and this way, and it's going to be negative and get steeper, which means right close to the top. What do you think we're approaching as we get closer and closer and closer to that, and finally that's the actual tangent to the vertex? What do you think the slope is going to be when we find the actual tangent of the vertex? It's going to be a flat line. It's the only spot on a parabola when you can find a flat line, which means that if you can find where the rate of change is 0, you will find the vertex. And interestingly enough, this chapter also teaches you that it's true for cubics. You will find what's called the maximum and the minimum if you can find where the slope is 0. And it keeps going for other polynomials. You can keep finding the tops and the bottom if you know where the rate of change is 0. That's going to be another thing that this chapter teaches you. So keep that in mind. As we get closer and closer to 15, the rate of change will be 0. So to test that out, I'm going to take the rate of change right near 0, which is going to be the g. I'm going to set it for m is equal to g of x minus h, so just to the left of it, minus, and I'm going to make my x 15 because we know we're looking at 15, minus g of 15, all divided by my h. Now let's just make our h 0.001, 0.001. Now we can see, and I didn't add enough zeros there, we can see that our m on the bottom right is getting closer and closer to 0. And that is because we're reaching a tangent that is a horizontal line at the peak. So that's good to know. Also, I'm on the right side because I accidentally am putting it in the wrong order. This should be actually to the right side. My bad. It should be g of 15 because g of 15 is the furthest right point minus the point just before it. And that makes it a positive slope, because this point is slightly to the left of that point, and that's how you will always want to do the slopes. You want to take the furthest right point and subtract the point just to the left of it and divide it by the h. Otherwise, you're going to flip your positive negative for your slope. And there you go. So let's keep going on, and then they just ask you some questions. What does it mean? What does that slope mean? What would the tangent line look like at the point of the maximum? Explain how you use tangents to find rates of change. So then they pull up this Ferris wheel. Now notice the Ferris wheel is in a cosine structure. Now before you ever move on, always grab the formula and have a quick look of what you should already know from transformations last year, because it repeats in calculus as well. So we have the Ferris wheels in height, and we see it translated cosine. So let's look at the y translations first. We have an amplitude of 5, and it's been elevated by 6, which means since my normal cosine usually starts up here at 1, comes down like that, goes back up to 1, and this goes down to -1 and +1 normally as the max and min. Since I'm adding 6 to both of that, when I add 6 to this, the max is going to be +7. When I add 6 to this, it's going to become +5, which means that's the new range, and this is the axis. So you start with that one. So now I know that, and actually I should have put it down there. I'm talking about something that's going to have an axis here. And actually, probably that's the first thing you should do. The new axis is always going to be this. Y is equal to 6. And normally the max and the min are going to be at +7 and +5. That's if the amplitude hadn't changed, but my amplitude has gone times 5, which means I'm going to be 5 above and 5 below the axis. And the axis was at y is equal to 6. So what's 5 below? Sorry, 5 above? It's 11. Axis. And what's 5 below that? 1. So that means this whole thing is going to go up to a max of 11 and down for 1. And now if I was to draw that really quickly, it would go like this, something like that. Now these are probably going to change because the period is changed right in there. How is the period changed? Let's look at the period first. Is it 4 times as big? No. It's not 4 times 360, which is the normal period. And by the way, in this course, you're probably going to be switching to radians, so 360 is 2 pi. We'll get to that. But it's actually a quarter of 360. What is a quarter of 360? It is 90. So that means this whole thing's going to go 90, repeat after 90 to 90. What have they? They're put it in time, so 90 seconds. And this -10 means it's all shifted to the right by 10. So that means my whole graph here, if I do it fresh over here, is going to start. So there's 0, there's 10, there's 90, etc. And actually I'll need 100. So normally it would go from 0 to 90, but instead it goes from 10 to 90. So that means it's going to start up here at 10 comma, what was the max we found? 11. 10 comma 11. And it's also going to finish over here, not at 90, but we moved it 10 to the right, so it's going to finish here at 100 comma 11. It's going to hit this bottom part at just above the x-axis, halfway through, because that's where the cosine does. Now normally halfway through 90 would be 45, but we got to add 10, so it's 55, comma, and what was the min point we discovered? 1. And it's going to cross the axis at the quarter point and the 3/4 point. So what's a quarter of the way through 90? 27.5 plus 10, 37.5, comma, what's the axis? 6. And then later on, 3/4 of the way, it's going to be 55 plus a quarter of the axis, which is 27. So it's going to be 70 or 82.5 comma 6, which means I'm going to have a weird thing like this. Let's see if I can. Nah, I can't really do it justice like that. I'll do it like this, and this isn't going to be very good, by the way. I'm going to go down, bottom, up, top. So when you have a knowledge, and you didn't have to do the coordinates like that, but I just wanted to show you the complete process. When you have the knowledge of the high points and low points now, you can answer a lot of the questions. And since this is his elevation on a Ferris wheel, it's quite clear that so it's 0 seconds, he gets on somewhere over here. But it's quite clear from the period we're discussing, it goes up and then down and then up and then down, and it will repeat every period. So that's another thing to keep in mind. It will repeat again every period. Now looking at a curve like that, look at the peaks and the valleys. That means the slope at the very bottom, the rate of change at the very bottom will be flat, and the rate of change at the very tops will be flat. So they're going to want you to start learning how to find the rate of change at peaks and valleys. Okay, let's go back. The question is, Shu thinks Leonard will be closer to the ground at 55 seconds. Do you agree? Well, did we draw the 55 seconds in there? Yeah, I believe we found that at 55 seconds he's at the lowest point. So yeah. And you can always punch this into Desmos to make sure. And so what they do is they take a t, they take one value for t at 54 seconds and 155, and they find the rate of change. Shows he's going down very slightly, almost zero. Then they take the rate of change just after that, and they find he's now going up very slowly, which means somewhere between 56 and 55, since we know this is a sine curve, the slope turned around. The slope was going down, and now it's going up, which means somewhere between this slope and this slope, it turned around. So it's a good indicator, but it's not proof yet. Saying could occur. Since the estimated instantaneous range is 0 since age 55. So then they reach a conclusion. So you would actually take much closer points to see how truthful that is. Then they do it again here where they just take a standard parabola and they want to know, show that the minimum value for this function is -2. So a very good way to do that is to just quickly complete the square without doing the second part, because all they want to know is the minimum value. And so if you partially complete the square, you're going to find the x value, which is what they're asking for, when the vertex. So how do we complete the square? It's already done partially. So I just half the 4. So it's x plus 2 is completing the square. I don't even have to do the rest because I've just discovered the x value. And how did I do that? It's half of this when there's nothing in front of the x, which there's nothing here, just a 1. Then it's half this value, which is +2 squared. And I don't have to figure out the rest because I suddenly have my x value at the vertex is going to be equal -2. Remember, it's the opposite for x values. And there, we've just proven it by partially completing the square. What they're doing here, though, is they're going to find the tangent just to the left of that and just to the right. And they're going to try to figure out if that's the case. Now, notice they don't even take the h value. They expand the equation with just leaving the h in there. They reach this conclusion, h squared divided by h, and is equal to h. So replace the values with small values of h to figure it out. So when h is really small, the m will be really small. So what they do is they're saying, well, if I can take tiny rates of value, tiny rates of change right near the peak, and it's heading one direction here, and heading the opposite direction the other way, then we can prove it. So you need to figure out if the rates of change are very close. So what you do is you would write on your piece of paper the formula. And completing the square just gave me a hint of what's going on. So -21, -21. Okay, so visually I know we already have the answers, right? So we don't really need it too much. But now I can just do a rate of change. I can say, okay, well, I'm interested in x when x is -2. So I'm going to take the rate of change just to the left of it. So what's just to the left of it? It's 2 plus h is just to the right of it. So I'm going to take the x of f of -2 and I'm going to subtract just to the left of it. -2 minus, and we'll make our h 0.00. I'll just set it for h so that you can see it. And I'm going to divide this all by my h. Now, if I set, oh, it's doing that again. So let's just make my h 0.0001 and my h 0, 0, 0, 1. And we can see my m is very small. So now we're going to take it just to the right of it. Now this you would all do by hand. You would find your f of minus 2, which is minus 25. You'd find your f of minus 2.0001, which is that. You would do 25, minus 25, minus minus, which becomes plus, 24.99999, which is that, and then you would divide that by your h, negative 0.00001. Did I take the left to the left of it? I believe I did. Yeah, it's going down. So I'm taking my 5 zeros, 1, and I'm dividing it by my h, which is 0.001. And we can see we get close to 0. Right there. And my bigger my h, the more this goes down, the more I can see I'm approaching 0. Then that's just to the left of it. That's a point just to the left of it. And then to the right of it, you would do the same thing. You're going to find, let's skip this formula and just do it by hand. You would find f of minus 2, which you know is minus 25, which is the vertex. Then you would find the point just to the right of it. What's the point just to the right of it? Minus 2 plus 0.0001, 3 zeros, and it's minus 24.999. So you're going to take the point just to the right of it, because you always take the point that's just to the right. You're going to subtract the point itself. Minus 25 becomes plus 25. Then you're going to take all of that and you're going to divide it by your h. And this all comes down to something we already figured out, which was the rate of change, instantaneous rate of change formula. And so we're going to divide it by our original h, which was 3 zeros. And you can see on the right side it's positive 0.001, which means the tangent at this point is indeed almost 0 and negative to the left. So it's almost 0 and negative on the left side, even, and I've exaggerated the tangent here. And almost positive, slightly above 0, and going up on the right side. So that's a negative, slightly almost 0 on the left, which we proved before, and it's positive on this side, almost 0 on the right, which means somewhere right in between. And since we've taken points that are right near 25, it's like 224.99999. That means the point right in between, which is 25, is probably a slope of 0. So by finding the slope of 0, we've essentially discovered the vertex. Then they're going to give you some problems to do, and they summarize it. And they show at the max and the min, you will find slopes of 0. And those are called local maxes and local mins, which they didn't cover here. But it will play an important role. So then they're doing all these questions. So let's start with 1. So we'll always identify the type of formula. It's running an assembly line. It's a parabola that's facing upwards. C of x is the cost per hour in thousands of dollars, and x is the number of items produced per hour in thousands. Both are in thousands, so we don't need to fiddle with them. The most economical production level occurs when 1,500 items are produced. Verify this using the appropriate calculations for rate of change. Well, first of all, it's an upward-facing parabola, so we're doing that. Cost efficiency, which is the cost of running, is we're trying to get the cost efficiency as low as possible, which means the minimum. So the question is that the minimum? Is 1,500 for x the minimum? So first of all, yes, we could just complete the square and see if our x comes out as 1,500. Oh, actually, this is giving our 1,500 as our y, because they're saying the most economic production level, which is C of x, not x. They didn't say the number of items. Oh, no, they did. When 1,500 items are produced, so that's our x. So they're saying our x value of our vertex is going to be 1,500 because that's the lowest cost of production. Yes, I could complete the square and figure out the vertex, but and that's a good way to verify your answer. But what they want you to do is they want you to take a value that's just to the left of 1500. So what's our h there? 0.001, I think. And they want you to take a value of x just to the right of it. So obviously this one is x minus h, and this one is x plus h. I added too many zeros on this one. And now to find it, we would take, for the left point, we take f of 1500, find our value of y for 1500. We subtract the point just to the left of it. And we all divide all that by our h, which is 0.001. So I would strongly suggest just taking a calculator, and then you take find your 1500 point first, so it's 1500 squared. Personally, this is why I use desmos, because this takes a long time. I'm going to multiply it by 0.3. I'm going to add it to 0.9 times 1500. And then I'm going to add 1675. And there I have my f of x, my f of 1500. So all I have to prove is that that's the bottom. So then you find your f of 15.00 or 14.999. Let's say this one first. And you're going to do this formula. You're going to take my f of 1500, and I'm going to subtract my f of 1499.999. So on a calculator now, what you would do is you would take 14, and actually make sure that you have the number that's using the same h always. So just take 1500 and subtract the h you're using, which I think has 2 zeros. Yeah, we're going to use 2 zeros in this one. Yeah, so we got it. And now we've just got to figure out what the y value is for that. So we square it. We multiply by 0.3. We're going to add 0.9 times 14. It's almost good to put the value 14.999 in memory. This is why I like to use desmos. And we're going to add the 1675. Now it's got to be very close to the result you got for the other one. If it isn't, you made a mistake. Okay, so we'll write that down. F of 1499.999 is equal to that. Is it very close to the other one? Yes, it is. It's just this one minus a little bit. And now we've got to do the subtraction. We've got to take this, and we've got to subtract that. So you can do it right in your calculator if you want. And this is, I should have just kept the numbers in there, but I'll just use the same ones. So 678.025 minus the 678.024 point. And you can't skip these. Like there's rules for rounding up. You're supposed to round up to the same number of decimals as your most accurate number. So that's my difference, and then I have to divide it by my h. Whoops. It's saying no, that's not true. Did I make an error? Did I make an error? 678.025 minus 678.024.0991003. Yeah, I don't think I did make an error. So that's the difference in them. Yeah. 0.001. So it's saying no, that's a big positive slope, and that's not the most economical. According to that, now I might have made an error. And again, that's why I like to use desmos. So we're going to put it right in here. And we're going to put c of x is equal to minus 0.3 times x squared. By the way, there are calculators you can bring into math class, especially university, that do what Desmos is doing, and they let you use them because they know you're not going to calculate these long formulas by hand, and if anything, you'll find it impossible. So you want to get your scientific calculators. 1500. Oh, did I get a minus wrong? Looks like I got a minus wrong. Yeah, I think I might have gotten a minus wrong. Yeah, I was adding my 0.9 instead of subtracting it. So there's my error. And you should also be able to see the graph. Yeah, there it is. Oh. Is it minus 3? No, I got it wrong. Yeah, it's not minus 3. It's plus 3. So maybe I didn't. No, I didn't get it wrong. And now I'm going to take my C14.99.999. And then I'm going to subtract them. So I'll call it B is equal to C of 1500 minus C of 1499.999. And I'm going to do that. And I'm going to take my B and I'm going to divide it by my H. So I did get the right answer. So that means if we find the value, now let's do the opposite one. Let's find our, so I did get the right answer. And it's a very steep positive slope, which means it's going up significantly at that point. If I know it's an upward facing parabola, and I know my slope is indeed positive 900, that means it's somewhere up here going there, which is not the most economical. I'm trying to find the bottom. So now we're going to take the point just to the right of it, which is this plus 0.001. And we're just going to essentially take C1500, or we're going to take that point, which is just to the right of it. And we're going to subtract the point C1500. Now we're going to take our B. And we can see that's also close to positive 1900, which means this is nowhere near the bottom of the vertex. It's a huge positive slope on both sides of it. And sure enough, if we take, we back up from the image, and we see that the point that's actually the vertex is at 0, and the point in question is, 1500 items would be C15. I don't know if they, I don't think they, I think 1500 items might be 1.5 actually, now that I see that it's in thousands of items. I don't know if they converted it or not. So the question is, yeah, no, the bottom of this is at 0. Which is, yeah, I don't know if we could have figured that out. So let's see if what the book came to a conclusion about. So I believe that's a no. Now I'm going to start pulling up the answers. It's 1.675. Okay. So that makes all sorts of sense now. Nope, didn't change it at all. But the big question is, did they mean 1.5? So I'm going to just use the formula and let. So I'm going to call it M2, and I'm going to use a point that's just to the right of it, which is C, just to the left of it, sorry, which is C 1.5, and it depends if they converted it or not, minus C 1.5 minus 0.001, which is my H, all divided by 0.001. So I can see, yeah, so it's a very small slope. Then I'm going to take my M1 and use a point that's just to the right of it, which is C 1.5 plus 0.001. And the big thing is, well, if the sign flips. minus C of, and it's not 5, it's 1.5. C of 1.5. So sometimes you can see how tricky they get. And all of it divided by 0.001. Got to get rid of that. And I can see, yes, sure enough, that's negative on this side, positive on this side. And if I zoom in, yeah, the new vertex is indeed there. And I did indeed have to take that 1,500 items and divide it by 1,000 because it's in 1,000 items. A little bit tricky on the textbook. And you can see where it's easy to do errors. I didn't have this written down correctly. So there you go. You just got to watch me make an error for 15 minutes. Here is obviously a coast curve. It's got an amplitude that's been reflected in the x-axis, and its amplitude is now 20. It's also been raised by 100. Models blood pressure in millimeters of mercury. What is the rate of change in blood pressure at 3 seconds? So what would we do here? I'm going to do it on paper first to show you what we do, and then I'm going to let Desmos do it, because obviously I can make errors that will just waste your time. So your secret is to take a point that's just to the right and to the left of that. So what's a point just to the left of it? 3 minus 0.001. What's a point just to the right of it? 3 plus 0.001. What's your h? It's the number we added or subtracted from it. So you're going to find the point to the left is going to be the p of 3 point minus 3p3 minus, so that's the rightmost point minus the point to the left of it, which is minus p3 minus 0.001, all divided by h, which is all divided by that. And the right point is going to be put here first, 3 plus 0.01. By the way, this comes out to 2.999 minus 0.3, all divided by 0.001. So if you discover your left point has, since this is a coast curve going up and down, you're not going to know if it's going up or down. If you discover that this is just positive and small and almost zero, and this is negative and almost zero, or vice versa, you know that it turned around in between those 2 points. You can also see right away that this whole curve has been 360 divided by 300, which becomes 3.6 divided by 3, which becomes 1.2, which means the period repeats every 1.2. It's not translated right or left. So that means the halfway point, it'll go 0 to 0.6 to 1.2. And if this is a coast curve, 0.6 should represent the bottom. And it is a coast curve, and it hasn't been shifted. So they're looking at a point that's at 3. So that keeps going. So it's going to 0.6. Does it ever become 3? Yeah, when on the 5th period it becomes a 3. See, every period, if I add 1.2, since the bottom's at 0.6, if I keep adding periods to it, every bottom after will be also at 0.6. So I get 1.8 as the next bottom. Then when I add 0.6, I get 2. Oh, sorry. Yeah, I got to add the period. 1.8, because the period is 1.2 as determined right here. The next period is going to be at 1.23, and that's sort of what they're looking for. So right away, by knowing the periods in the graph, I do indeed know that a bottom will occur at 3 seconds. So that helps just to verify my answer. So I can do the calculations here. You would put 3 into this formula, figure it out, 2.9 into this formula. We might as well. So how do you figure out the 3? You put 3 in for t, and you actually multiply it by the 300, and then you take cos. 3 times the 300 And then you got to go to your trig and you take cos. Minus 1. Okay. Then you have to multiply, so it's always just order of operations at this point. Next, we've got to multiply by minus 20. Comes plus 20. Next, we've got to add 100. So that means that's my my blood pressure, 120, at that point. So that means at P of 3, my blood pressure is 120. Next, let's find our P of 2.999. So again, I just take my calculator, and you follow the order of operations. I'm going to take my 2.999 times 300, and then you hit equals, and then you got to take the cos of it. Very close to -1. Then I got to multiply by -20, and then I've got to add 100. So there's my. Okay. Then I got to find my P of 3.001, which is my point just to the right of it. And you do the same thing. You take 3.001 and you follow the orders of operations. You're going to multiply by 300 in the middle. Then you're going to find the cos of it. Then you're going to multiply by minus 20. And then you're going to add 100. And you can see I get a number that's just below again. Now what's interesting is, visually, you should be able to see that this number here is lower than both these. And both of these are the same, which implies that it's come down. It's hit that first number here. Then it hits the 120 at a lower number. And then it comes back up to that number, 119. Almost automatically indicates, since these are on equal sides of 3, that the bottom will be 120. Almost automatically. But let's look at the rate of change now. We're going to take rate of change 1. Rate of change left point is going to be 119. They're both the same, right? It's going to be 119, 99972, whatever, 58. And it's going to be minus 120, and it's all going to be divided by 0.01. And the other one's just the reverse direction. It's going to be 120 minus 119. And actually, no, the left point is indeed this one. Since they're both the same number, it's just the order that's done. Why is this the left point? Because you always take the rightmost point, subtract the leftmost point, and divide by h. And to find the rightmost point rate of change, you take the rightmost point, and you subtract the point you're interested in, and you divide by h. Now, obviously, one's going to produce a negative, and one's going to produce a positive. They're going to be the same number. And there's really no point in doing it. Just, we're going to do it once, and just keep in mind that the signs are going to switch, depending on which order we do it in. And here's where you should have just saved your results. Okay, so we'll do this one, which is the rightmost point. Divided by h. And keep in mind our results will be the same, just the signs will switch. Probably did a slight error there. Probably should have been closer to 0. So I'll try it again. Oh, I know what I did there. It's not 199, it's 120, it's 119. I'm looking at the wrong number there. There we go. Okay, this is the rightmost point. Minus 120. You get an obscenely small number, but it's going to actually get bigger when I divide it by a smaller number. Yeah, okay, so it's not quite 0. So I probably should have taken an h that's more. That's, you know, smaller than that. If I'm to graph it, you get the same idea. Blood pressure based on time is equal to negative 20 cos 300 t plus, what was the plus? 120? Was that the plus? Plus 100. Very hard to see it. Get rid of this. Get rid of that. I'll just keep one of these. And it would help if got rid of that. Yeah. So if you look at that, you see it's a sine curve that's repeating over and over again. Quite quickly. And now just let it do the equation for me. I'll take the slope of the point just to the left, which is going to be, so it's b of, was it 3? Yeah. So I'm going to take b of 3 minus b of, let's take a really big h, 0.00001. And we're going to divide it by that same h. And there we go, that's more accurate. So I just needed to take a bigger h, and I can see my slope is changing. And to just get a better idea, I'm going to just take the 2.8 is smaller than x is smaller than 3.2. And we'll say, see if that t. So we're just going to see if we can see that. Oh, smaller than t. Yeah. There it is. There's the question. And we're just going to see if the top part is indeed at 3. Yep. So that is good indication. The left side, especially since the left side was positive and the right side's negative, there was a turning point at some point. Okay. And to take that right side instead, I can just go back and switch these around. And take this as plus, that's the right point, the point to the right of it, minus b of 3. And we can go back here and put that as t. Undefined, so this is the right point minus the left point. Oh yeah, I've got to get rid of the limitations. There we go. And I get, see, this is negative on this one, and it was positive on the other, with the same number. So if it's changed slopes in positive minus, it means it turned at some point. For a slope to suddenly go from positive on this side to negative on the other, it means it had to turn. Turning point. So if you find points positive and negatives on either side of the point, somewhere in there is a turning point. Kind of what they're getting at. So then they go on. Then they do a function. What do you know about the slopes of the tangent lines of the following points? Interesting. If there's a maximum value at this fictional point, what do you know about the tangent lines at the following points? Ah, that's a good point. So if we're talking about a maximum, we're talking about something like this. On the left side of a maximum, the slope will be positive, and on the right side, the slope will be negative. It's very obvious. Not so for a minimum. For a minimum, on the left side, the slope will be negative, and on the right side, the slope will be positive. So then they're asking right here, the point on the left and very close, well, left of a maximum, it's going to be positive. To the right of and very close, it's going to be negative. Then they do the reverse with a minimum, and they ask you the same thing. So that's a very good point. So when you're at a maximum, the point to the left will always be positive, and the point to the slope, the tangent slope, will always be negative to the right. When you're at a minimum, the slope to the left will always be negative, and the slope on the right side will always be positive. Remember that. It is definitely useful. Then they get you to practice. For each of the following points given is the point given is the maximum. Use the difference quotient to verify. So essentially they're telling you for sure this is the max or the min. This is an upward facing parabola, so we're talking about a min. So that means the point to the left of it, so we're talking about x value of minus 6. So the point to the left of it is minus 6.000001, and the point to the right of it is minus 5.99999. So you would put that in, you would plug both those values of the equation to get the y values, then you would use the slopes equation over and over and over again. Now what I'm instead going to do is I'm going to keep this like this. I'm going to just call it F and F. And we're going to call this an A value, and they're going to give us the A value. Then up here, we're just going to construct our f of x graph over and over again. So what's the first one they gave us? The first formula they gave us is this one. 0.5 x squared plus 6x plus 7.5. And the point in question that they've given us is minus 6. They've said minus 6 is the x value. So we're just going to put in minus 6 here over and over again. And we're going to put in minus 6. And we're going to just keep this y small. We're going to get rid of that. And we can see the slope is positive and very small on the point that's just to the right. We're going to copy the formula. Oops. I'm going to copy the formula. And we're going to take a second point. That's just to the, this point was just to the right. And so now we're going to take one that's just to the left. There we go. Now notice the slopes are the same, which indicates that we have an exact middle point of minus 6 in the middle. But notice the slope is positive up here on the point that is to the right, and to the left, this is the left point, and we're taking the slope of the point between the main point and the left point. It is negative, which implies that, indeed, as we saw here, anything to the left is positive, anything to the right is negative. This isn't therefore a maximum, because the point to the left is let me make sure. This is the point to the right. It's positive. Oh, did I get it wrong? Yeah, I did get it wrong. I got it switched around. This is the point to the right. So I should have just done this. Oh, sorry, no. This is the point to the left because this is a bigger negative number. So I should have actually switched it around. This is the point to the left. And this is the point to the right because yeah. Let's see, this is to the left of it. Yeah, because this is a bigger number. So the slope is negative, is that right? We're taking a point, and we're taking the slope between the main point and a point to the left of it. Should be negative. Oh yeah, so yeah, we're not a downward facing, we're not an upward facing, this is a min. Yeah, so there we go. That is the point in the middle, that is the point to the left of it. Which means in this one, I've got to take the point to the right of it, which is, I totally got that wrong. It's this. Not my best day. And it's that. So we can see that they are indeed opposite and the same values. So this, if we look at it, sure enough, all the values to the left of this point are going to be negative slope. This is indeed a point to the left of point -6, and its slope is negative. This is a point that is indeed to the right of -6, and its slope is positive, which means, sure enough, there's the negative graphically proven that that's probably the minimum. You can see how it's easy to make a calculation error. Minus 6x squared plus 6x plus 9, so that's a downward facing parabola, which means to the left of 0.5 it should be downward facing is going to be positive, and to the right of 0.5 is going to be negative. So now I'm just going to leave the equations in there and do this. Minus 6x squared minus 6x plus 9. And the values in question are 0.5. So now all I have to do is take this 0.5, and you can even do this. This is a lot easier. And it said negative 0.5, didn't it? No, just 0.5, so get rid of the negative. And we're taking, this is a point to the let's take a point to the left. So it's going to be f.5 minus your h. So you don't even have to calculate it. You can just put your minus h right in there. And let's make sure I got the formula right. Minus 6x squared plus 6x. There we go. You're probably all screaming at the screen. So we get a positive slope on the left side between this slightly point to the left and the middle point. And then we can do the same here. So I'm just going to copy this, and the secret is I've got to reverse it. I've got to take a point that's now to the right side and subtract the middle point and make sure I call it M2. Very good. And did I get my zeros right? Yeah. Interesting, that should have been almost exactly like that. It looks like I have my zeros. I think I have one too many zeros. Yeah, I got 3 zeros up here. There we go. So this point is a point that's just to the right of it, and the slope is negative. And this is the slope that is just to the left of it, and slope is positive. If you can't see that that this point is to the left of it, it's because I've taken the same value of x and I've subtracted a little bit of it, which means I have to be to the left of this because I've subtracted it. In this case, I've added a little bit to 0.5, so this point is slightly to the right of 0.5, and I'm subtracting the 0.5, and that's because I always have to take the rightmost point, which in this case is 0.5, and subtract the leftmost point. And I have to take the rightmost point here, which is the one adding 0.01, and subtract the 0.5. Don't get these formulas mixed up. This was reviewed in the last 2 sections ago. It's very important. So it's essentially, I can't stress this enough, when you're examining any point, let's call it point P, the point just to the left of P is going to be P minus H. And the point just to the right of P is going to be P plus H. You then have to figure out what point P you're looking at. Let's say that P has an x value of 2, which means your point value just to the left of it is 2 minus H, and your point value just to the right is 2 plus H. Now let's say you're doing 0.001 for H, but the smaller your H, the better, which means this one is going to be 1.999, and this point here is 2.001. Now remember that this point is to the left of point P, and this point is to the right of point P, which means that if I'm going to examine the slope of a point that's to the left, I must take point P and subtract the point that's just to the left after I figure it out within the formula and divide it by the H. If I'm looking at the other point to the right, which is this point, then I must take that point within the formula, so it's the f of 2.001, and subtract the f of 2. It is very important that you always get this right. You're taking the main point and subtracting the point to the left, and you're taking the point to the right and subtracting the main point. And that's because if you don't, your m values will go from positive to negative, and you'll get the wrong result. And it continues to do it for 5 sine x at 90 degrees. So 5 sine x. And so again, we're taking a point that's just to the left and just to the right. You can see you might say, oh, that's a bigger than 0, but no, it's times exponent of 10 to the negative 9, so it's ridiculously small. So if we get an h a bit smaller, we might be able to see it, calculate it for. There we go. Oh, still did it. Let's take an h that's smaller. Take an h that's smaller. Oh. Yeah, there we go. now you can see it with the 0. So this point is on the right side of it, and the slope is negative, so it's going down, and the slope is on the left of it, and it's positive. So that means the turning point happened at 90. And sure enough, if we can see it, it's right there. Because the slope to the left is positive and the slope to the right is negative, we know that that must be a maximum. And that's what you're learning too. Which one's negative? And I should have covered it on the other ones. How do you figure out when it's a maximum? Well, if the slope is positive on the left and negative on the right, it's a max. And the last one's minus 4.5 cos 2x. Okay, and this time they're not interested in 90 degrees, they're interested in 0 degrees. So we're going to take the point 0 and subtract the point just to the left of it, and the point 0 to the right of it, and subtract the main point we're interested in. Now, the slope just to the left of it is negative, and the slope just to the right of it is positive, which means we're talking about a minimum. We're talking about a minimum. Sure enough, if we go to 0, it's down at the bottom. So the slope is going down, down, down to the left, and then up, up, up to the right, and that only happens at a turning point. So if your slopes suddenly switch sides, there's a turning point somewhere between those points. And they want you to get good at it over and over again. Use algebraic strategy, verify the point given for each function is either a max or a min. So algebraic strategy would mean you punch it into the formula. This one says use the different quotient. So this one we would probably find the vertex, because we're dealing with upward facing parabola, downward facing, upward facing. This we just have to know our cos. This is a cubic and another cubic. Interesting. Well, imagine if you could go on point either side of it and get either a smaller or bigger y, you will prove that this has reached a bottom. That's another way to do it. If the y value is at the highest here and it's lower on either side of it, and you know the curve, then you know that this was probably max. As an example, if I know I'm dealing with a sine curve and I'm looking at this point here, which is a max, and I take a point over here and find the y value is smaller, and I take a point over here and I find the y value is smaller, since I know the nature of a sine curve, I have to assume that this point is higher than either of those. And if I get really close, I can really determine it. So that's algebraically how you do it. I don't know if that's what they want you to do, but you could also do it with vertex algebra for some of them, and factoring. So let's practice our algebra. So let's find the vertex of this. Let's see if you can do it. The secret's in the middle. You can ignore the number for now. So to find that, it's going to be x minus 2 squared. If I were to expand x minus 2 squared, I get an unlikable plus 4, because it becomes x squared minus 4x, then there's this plus 4. Which means I created a plus 4 I didn't want, which means I have to subtract 4. And since I'm adding 5, what's minus 4 plus 5? By the way, I can do this because there's nothing in front of the x squared. So I get here becomes plus 1. So I can see that indeed becomes this plus 1. Which means, what's my vertex? My vertex is right in there. It's plus 2, comma 1, which is right there. If we're dealing with an upward facing parabola, then I found my minimum using algebra, that it's plus 2, comma 1. What about this next one? Same thing. We have an x squared that has a minus 1 in front of it, so we want to get rid of the minus 1. I might have to stop after this one and do a part 2. So when I take out the minus, all the signs change. So I get plus, plus, and minus. So that means I'm dealing with a minus 1 out front, and then an x squared, my plus 12x, minus 5.75. Now, this is a tricky one. So we're going to focus on the middle, and we're going to push this all the way to the side. We're now going to create square brackets. minus 1. And how do I create x squared plus 12x? Well, that's x plus 6, the half of it, squared. And what's the thing I create that I don't want? Well, it's plus 6 times plus 6 is 36. So now I have to have, let's put the square brackets over here. Now I have to subtract 36. And if you're not up on your completing the square, get up on it. And don't forget to leave this here over there. Now that minus 6 has to come out of the square bracket, minus 36. So I have to multiply by this minus 1 to get it away from this. So I get this minus 1, x plus 6 squared, and I'll get to that in a second. And then it finally comes out as plus 36 minus 3.75, and that becomes 30.25. And then don't forget the square. Now let's see if we got the vertex. No, we didn't. Plus 36. Half that, 6, 12, 18, 36. 6, 36, it was minus 1. I think they might have got it wrong. Let's just plug it right into Desmos. No, they got it right. So my thing needs work. So back to the drawing board here. Oh, yeah, it's got it. That's how it does it squared. And it's minus, right? So when I take the minus 1 out of the front, I get x squared plus 12x. And over here, I'm just leaving the 0.75. Oh, I know what I did. I shouldn't have been changing the sign of this 0.75. I'm only taking the minus 1 out of the first two terms. And that means the second term stays as a positive because I'm not factoring out the minus 1 from the 0.75. It was just supposed to stay there as is. I'm only factoring out the minus 1 from these two. If I do it from minus 3.5, I have to subtract it from the 36 as well, which makes minus 41.75, and then it gets multiplied by minus 1. So that was just a factoring error. I had to leave that outside of the minus 1, like that. And then over here I get minus 1, x plus 6 squared. And it's all in its own square brackets, and I create an unwanted 36, so I have to subtract 36. And on the outside of the box, I still have plus 5.75. So when this minus 1 kicks the 36 out, I get 36 plus 5.75, which gives me indeed 41.75. And I can see the x vertex right there. So I'm making a lot of errors this morning, so I'm going to stop after this and get a bite to eat or something. So algebraically, what's going on with this? This is a coast curve, and the only thing is the amplitude has been increased by 3. That's the only thing that's happened. So since we normally know a coast curve starts at 0 degrees, at its max goes down, and the max is normally 1, this 3 makes the max now at 0, 3, which is indeed one of the maxes here. So this is really all about identifying your curves. This next one looks scarier than it is until you see that you can factor out something. You can factor out an x from both of them. I get x and x squared minus 3. Okay. Which means I have a 3 points where they hit the x-axis. The 3 points are x is equal to 0, and the other points is x is equal to the square root of 3, and x is equal to the negative square root of 3. Root of positive 3. It's a negative square root of 3. So just the question is, does that fall in between -1 and 2? So algebraically, you could instead plug these numbers in, or I can also find the factors. Well, I did just find the factors of that. But trying to find the max point of that would be interesting. So this is a, oh, I know what it's, yeah, I know it's not doing that. It's plus square root of 3 each time, I think. I think this all, because this is positive, it's coming down from the left. It's going through 0. And then it's coming back up through this. And that's very hard to see. No, actually I don't. I think it's coming up through the square root, coming down to 0, going up through the square root. So 0, square root of 3, negative square root of 3. The question is, -1 going to be a max or a min? Ah, there's our answer. Because all cubics start in quadrant 3, go up, go down, go up. Since I can factor it out and figure out it must go up and down and up, I know that this point, if they're telling me it is a max and min, which they are, and that I know negative square root of 3 is one of the factors, and you can figure that out here. The other factor is 0. The other factor is 0. So how did I figure that out, actually? Let's get on to that. Once I factored it out, I had this. Okay? And there's a big old square there. Right there. So the question is, when is y 0? That's when it touches the x-axis. When is y 0 in this case? Well, clearly, when x is 0, it will make the whole thing 0. So one of the answers right away is x is 0. The next question is, the other time it's 0 is when this bracket is 0. So that means x squared minus 3 in the bracket must be equal to 0. When I solve for x squared, I get x squared is equal to positive 3. But when I take the square root of x on both sides, I get x is equal to plus or minus square root of 3. And that's because when you take the square root of x, you must instantly take the plus or minus, which means it's going to cross these points here at positive square root of 3x, comma 0, and it's going to cross the x-axis over here at negative square root of 3, comma 0, which means it's going to go up, turn around right here, go through 0, comma 0, which I found out from this, 0, comma 0, which means the maximum, if they're telling me, is -1, which is between 0 and square root of 3. Square root of 3 is like 1.222212 or something. Then that must be a max point, because the cubics always go like that. Complicated. That's when you have to know your cubics and go back to what you know. Now, what about this one? This is a negative cubic, right? It's going to go down, come up, and go down, which means if they're telling me 2 is either the max here or the min here, we would just need to know a couple of the points. Well, the question is, can we factor any of that? We cannot really factor this, and I don't believe they've taught you how to factor cubics yet. We know when x is 0, the whole thing's -1. So when x is 0, the whole thing crosses the y-axis at -1. So that's one thing we know. If we were to plug 1 into here, we get -1 plus 12 minus 1. So we know -1 is not working. Sorry, -1 minus 12 minus 1. If we put plus 1 in there, we get minus plus 12. Minus 1 doesn't work. Negative doesn't work either. So -1 isn't a good factor. I don't believe they've taught you how to factor this yet, so I don't want to show it to you unless they've taught it to you. We'd have to do either long division, or we do need to find a root. 0 is not a root. There is a quadratic formula for cubics, but that's university level. -2, this becomes, so we want a positive, I think. We want a positive every time, because the negative x will stay negative and then become positive, and this will become negative. So I think we want a negative. So we just have to figure out what number of x would create this. So a 2, 4, 8, no. 3, 27, way too big. So if it was -2, we would get +8 minus 12 minus 1. Doesn't work. If it was -2. +2 doesn't work at all. Oh, +2 can work too, yeah. 3 would create a 27. Oh, that might work actually. -36 minus 1, almost. So that's just too many factors going on here. There's definitely a trick that I'm just not seeing. And you can't factor out an x. Usually you try to find one of the roots. Usually by plugging in 0, 1, 2, and 3. And I might have to just cheat, just to give myself a hint. Well, maybe they have taught you how to factor out. So let's try 3. And then -36, not 3. Let's try 4. No, it's never going to be that. So that's not going to do it. They've given me 2. Oh, I know I can do it. Jesus, what am I thinking? I'm going to just take the 2 and put it into there. So 2, if I put 2 into there, I get -8. Because 2 cubed is going to be +8, but then the minus makes it -8. +24 -1, which becomes -9, 15, +15, right? So they already gave it to me, +15. What's the point just to the left of it? Well, let's take 1. What's the point just to the right of it? Let's just take 3. So we know this is going to be either a peak or min. So let's take 1. So 1 cubed is 1, times -1 is -1, plus 12 is +11, minus 1 is 10. So that means 1 is 10. Is the y higher or lower than the 15? It's lower. Now let's take 3. 3 cubes 27 times -27 plus 36. So that's +9 minus 8, 8. So we get 3, 8. Both these y values are lower than this, and they're on left and right side of this value, which means 2, 15 is the max. That was stupid that I didn't get it that quickly, and thus I am tired. There's a good 8 more questions, and they're all important, so I'm going to stop there. Very long play at double speed.